Lesson on probability formulas. This is video 3 of 3 videos. This part 3, concentrates on the topic of probability tree diagrams. As you may remember, in video 2, there was discussion about what are called independent and dependent events. Tree diagrams can be used to help solve problems involving independent and dependent events. They are a very useful way to visually show dependence and independence. Let's begin with this example. Peter has 10 colored cubes in a bag. 3 of the cubes are red, 7 are blue. He removes a cube at random from the bag and notes the color. Before replacing it, he then chooses a second cube at random. Okay, so the main thing here is that he chose a cube from the bag, made a note of the color, and then replaced it back into the bag. So the bag has been reset. So the effects of his first draw of a cube has no effect on the probability of his second draw. So this is an independent situation. The second probability does not depend on the first thing. So let's take a look. His first choice. There are 3 red cubes, so he has a 3 out of 10 probability of drawing a red cube. So a tree diagram looks like this. We can show the choice is here, and then the different paths that are possible from that choice. The other path there is a 7 of 10 probability of choosing a blue cube. So here we have the 2 options. Now we are sitting here, and our path continues. If he chose a red first, now in his second choice of a cube, he can also choose a red or blue again. And likewise, if he chose a blue first, he also has a second choice, which is going to be either red or blue again. So this part here represents the same action, but it's shown twice because it follows the first action. Okay, so in the second choice, since the cube has been replaced back in the bag, this has been put back in the bag, there is still a 3 out of 10 chance of drawing a red. And there's still a 7 out of 10 chance of drawing a blue. On this end here, the numbers are the same because, again, even if you drew blue first, he replaced it in the bag, so the chance of getting red or blue on the second choice of a cube is also the same. Now, each of these paths represents, so there's a 1 path here, another one, 3, and 4. There are 4 total paths here. Those 4 total paths show all the possibilities of events that could happen. So the first path of choosing a red and red, the probability is red and red, so we multiply. We learned that relationship last time. We multiply those and we get a 9 out of 10 probability. The next path, red and blue, is a 3/10 times 7/10 probability. 21 out of 100 is the result. Third path, blue red, you multiply probabilities to get that. And fourth path, blue, 7/10 times 7/10. So that is the highest chance. The highest chance of drawing a blue followed by a blue is 49 out of 100. And that makes sense because there's so many more blue pieces in the bag. Notice all these probabilities should add up to 100. 9 plus 21 is 30. 30 plus 21 is 51 plus 49, 100. So these paths cover all the possibilities. Therefore, adding them up shows 100% probability occurrence. In other words, it is certain one of these will occur. Okay, now looking at dependent events. So same situation. 3 cubes are red, 7 are blue in the bag. However, he removes a cube at random from the bag, notes the color, but does not replace that cube. So again, this shows dependence. His second selection probability is now dependent on what happens in the first draw. So let's take a look. Again, the first choice is unchanged. There are 3 out of 10 reds and 7 out of 10 blues, so those are the probabilities. Now the second choice, however, has changed. If he draws a red one, there is now 1 fewer red piece in the bag. So now there are 2 red pieces left only out of the 9 remaining because, again, 1 has been removed. For blue, there are still 7 blue remaining, but out of 9 possible cubes in the bag because the bag now has 9 cubes instead of 10 cubes remaining. Okay, let's look at blue then. See if you can fill these in for blue with the same kind of thinking. These are the probabilities you should have gotten here. If he chose a blue first, now there is 1 fewer pieces in the bag, so the denominator is 9 for both. However, the red is still the same. There's still 3 red left, so 3 out of 9. The blue, however, has been reduced by 1, so 6 out of 9. This is a simple but key concept in probability. Make sure you really understand the diagram and what it's showing here. The probability of following the red-red path is now this. It changed from before because, again, these are now dependent probabilities. The probability of red and blue is this, blue and red is that, and then what is the probability of blue followed by blue? Okay, hopefully you got something like this, and there we have our probability. Again, the odds are higher than in the previous example because there's less cubes in the bag after the first draw. Okay, let's look at another example like this. Peter and Becky run a race and play a tennis match. So first they're going to race, and then they're going to play a tennis match. So it's like one event followed by another event. The probability that Peter wins the race is 0.4, so it's drawn here. Peter wins 0.4. The probability that Becky wins at tennis is 0.7. Those are the only pieces of information we have. So what we know is there's a 40% chance Peter will win the race. So then what is the probability that Becky will win the race? Well, hopefully you got 0.6, because those two together are all the things that can happen, therefore they have to have a probability of 1. Now, the probability Becky wins in tennis is 0.7. Where will that go on here? Well, that's going to go right here and right here. So Becky wins at tennis is here, Becky wins at tennis is here, and then again, these have to make 1, so probability that Peter wins at tennis is 0.3, 0.3. All right, so a question. What's the probability Becky wins at least once? So first thing I'm going to have you answer is how many, again, there's 4 total paths here, but how many of those paths represent the situation where Becky wins at least once? Okay, hopefully you were thinking 3. Here is one path that leads to Becky winning once. So first Peter wins the race, but then she wins at tennis. Here's another potential path. Becky wins the race, but then Peter wins at tennis. So that's 2 paths already. But there's also a third path. It is the path where Becky wins both. And even though this says Becky wins at least once, it doesn't say Becky wins once. It says at least once. So that means she has to win once, or she can win more than once. In other words, she can win both times. So 3 of these 4 paths lead to the situation of her winning at least once. The only path that does not show that is this top path, which is Peter winning both times. And that means she does not win at least once. So now when we're looking for the probability that Becky wins at least once, we need the probability of all these paths. So first find the probability of each path, and then what do you do with those 3 probabilities? What do you think? Let's try it out. Okay, so we have probability that we have Peter wins, Becky wins, or Becky wins, Peter wins, or Becky, Becky. So that's basically showing the 3 paths. Peter, Becky, Becky, Peter, or Becky, Becky. All right, so we have this union here showing that we're going to combine all those probabilities. Here's the first path, here's the second, here's the third, and hopefully you made the mental jump to recognize we're going to add those because we want to know the probability of that path, or the probability of that one, or the probability of that one. So we just add all those probabilities to get a total. So here's each path, and here's the total. So the chance that Becky will win at least once is 0.88. There's a very high probability. There's an easy way to approach this problem. The easier way is this. Rather than looking at the 3 paths, figuring those out and adding them up, can't we just say, well, there's only 4 paths possible, so it's easier to calculate the path that does not show this situation, which is the Peter-Peter path, and we just do 1, because all of these, again, they have to add up to a probability of 1. So we can just do 1 minus the probability that Peter wins on both. And the probability Peter wins both is 0.4 times 0.3, this path. And 1 minus that is 0.88. Notice the answers match, as they should. And this approach, once you understand exactly what it means, is much easier. Okay, last problem. We have the probability that Samuel, a keen member of the school archery club, hits the bullseye. So I guess he's shooting some arrows, and he has a good probability of hitting the bullseye. He's a very good archer, 0.8. Samuel takes 2 shots. Assume that success with each shot is independent from the previous shot. So it tells you about independence here. So if he does well on the first shot, it does not change his probability for the next one. In real life, maybe that would be different. If you get a bullseye on your first shot, you might be more likely to get a bullseye on the second because your confidence has been built up. Or likewise, if you miss on the first shot, maybe your confidence has gone down a little bit and you're more likely to miss on the second shot. But in this case, we're keeping it simple. He has a consistent probability of 0.8 of making the bullseye. So what you need to do is draw a tree diagram and then calculate these three probabilities. Okay, let's check your work here. Here's the tree diagram. This represents his first shot, this represents his second shot, and we see hit hit, hit miss, miss hit, or miss miss. Anyway, check your tree diagram and then check your work on all three questions. This is a pretty typical question of this type. It's important that after the work you've done on these three videos that all these questions here make sense. Exactly what has happened makes sense to you. All right, good luck with that. There are no assignments that follow these videos. We'll continue with this topic next time we meet.